All right, so I'm on page 12 of your packet. Now, one-to-one functions. They're pretty easy because it's one-to-one functions are a function, but it's more of a subcategory of functions. All right. So first off, before we get into one-to-one functions, can anyone tell me what the main characteristic of a function is? So in other words, what's the one thing that has to happen in order for it to be considered a function? So in order for a relationship or an equation to be considered a function, what has to happen? The x's cannot repeat. So if the x values don't repeat, it's considered a function. All right. If we were looking at a graph, how do we know that graph is considered a function? It has to pass the vertical line test. Meaning, if you ran your pencil vertically along that graph, at no point should two places on the graph cross that pencil at once. All right? Because all the vertical line test checks for is that there's no repeating x's. If you have a graph where it hits your pencil in two different spots, the x is repeated. All right? So, just to recap, in order for something to be considered a function, no repeating x values, and it has to pass the vertical line test. And those two things are essentially the same thing. It's just depending on what you're looking at. If you're looking at a table of a function, none of the x values should repeat. If you're looking at a graph of a function, it should pass the vertical line test. Now, the category of function that we're talking about is one-to-one. So, let's look at an example first so we can figure out what one-to-one actually is. All right. So the first example, we have two different functions. We have f of x, which is 2x, and g of x, which is x squared. And we got to map the function with a domain of -2, 0, and 2. Now, can someone remind me what domain is? Someone besides Abigail. What's domain? So it's left to right. So that would be what values? X values. Good. Range is Y values. So when we're saying domain, we're talking X values. So we're saying if we have these X values, what's our range? Or in other words, the Y values. So we've already done this before with evaluating. How do we get Y values from the X values? What do we do for warm-up today? How do we get the Y values given the X values and the function? Just plug them back in for the function. All right. So for f of x, all right, f of x is equal to 2x. So all we got to do is do what to each of these x values for f? So if we plug it in, what essentially am I doing? What's the only thing that I'm doing? Multiply by 2. So I just have to multiply all of these functions by 2. So what is -2 times 2? -4. 0 times 2? 2 times 2. Now, this is what we call a function map, these ovals. And how it works is that we're going to draw arrows that connect the x values to their corresponding y value. So in reality, you should only write a number in each oval once. All right, so if it repeats, you would just draw 2 arrows to it. So all this is saying, this is how you read it. If I have an x value of -2, that means I have a y value of -4 for this function. That's what those arrows mean. All right. Domain of g. g of x is equal to x squared. So what's the only thing that I'm doing to these three numbers? Squaring them. So I'm going to square each number. What's negative 2 squared? Positive 4. What's 0 squared? What's 2 squared? 4. Now, since 4 repeats twice, we're only going to write 4 once in the other circle. So you should only have 0 and 4 in the current oval. Now, we're going to draw the arrows to those y values. So negative 2 goes to 4, 0 goes to 0, and 2 goes to 4. So you should have 2 arrows pointing towards 4. So, first off, can I consider both of these functions functions? Yes, because there's no repeating x's. Now, remember what I said earlier. It doesn't matter if the y's repeat. They're still considered functions, even if the y's repeat. So even though in the domain, even though in G we have repeating y's, it's still considered a function because the x's don't repeat. However, in a one-to-one function, both the x's and the y's cannot repeat. All right. So, what is fundamentally different between these two functions in terms of how the elements of this domain get mapped to the elements of the range? So, what's the main difference between So, what's the main difference between what's being mapped to this range and what's being mapped to this range? Say it again, boys. There is repeating y. So, in other words, for this function, each x has their own y. But for this function, 2 of our x's share a y. All right. So that's the difference. So f has no repeating y's. But G does. And so again, that's what leads me into one-to-one functions. So with one-to-one functions, first off, it's got to be considered a function, so no repeating x's. So a function's called one-to-one if no x's repeat and if no f of x is repeat, which, remember, f of x is another name for y. Good. So that means y1 cannot equal y2. That's another way you could write that. So in other words, it's a one-to-one function if there's no repeating x values or y values repeat. So no x values or y values repeat. Now, don't get this confused with if it's just a function or not. One-to-one is a subcategory of function. So first off, every one-to-one function is going to be a function. All right, every one-to-one function, the x's will not repeat. But not every function is one-to-one. So it's kind of like that analogy, like every square is a rectangle, but not every rectangle is a square. That's kind of how this is. Every one-to-one function is a function, but not every function is one-to-one. All right, does that make sense? So let's go down the line. All right, we're going to do a little activity. So we're going to look at these tables. All right, and we're just going to go down the line. And I want you with a thumbs up or thumbs down. Thumbs up if you think it's one-to-one. Thumbs down if you don't think it's one-to-one. So in other words, if the x values repeat, it's automatically just not a function. You can throw it out. But if the x values don't repeat, check the y values. If they repeat, it's not one-to-one. Okay? So take a minute, look at number 1. When I tell you to, thumbs up, thumbs down, you think it's one-to-one. 3, 2, 1, go. Good. It is not 1-to-1. Is it even a function? Why? Those two x values repeat. So it's not even 1-to-1. It's just not a function. Look at 2. All right. Thumbs up, thumbs down if you think it's 1-to-1. Take a minute, think about it. 3, 2, 1, go. What do you think? Is it 1-to-1 or is it not? It is not 1-to-1. Now, is it a function though? Yes. None of the x values repeat. But what makes it not 1-to-1? 2 of the y values repeat. So the 1 and 1 of the y values, those repeated. So it is a function, but not 1-to-1. All right, look at 3. Take a minute, think about it. All right, thumbs up, thumbs down if you think it's 1-to-1. Ready, go. Good, it is 1-to-1. Why? Nothing repeats. All right, so this one is 1-to-1. All right, the last one. Take a minute, look at it. All right, thumbs up, thumbs down if you think it's 1-to-1. Go. It is not 1-to-1. However, is it a function? It is not a function. What makes it not a function? Those negative 2's repeat. So, guys, if it does not, so here's the easiest way to figure out 1-to-1. Start by looking at the x values just to see if it's even a function. If it's not a function, you don't even have to worry about looking at the y values. Because a 1-to-1 function, it's in the name, it has to be a function. But if it is a function, that's when you look at the y values and see if they repeat. If they do, it's not a 1-to-1. If they don't, it is a 1-to-1. All right? That's what 1-to-1 means. One x value to one y value. That's why we call them 1-to-1. Does that make sense? Yes, no, maybe? Yes. All right. Now, next thing we're going to do is graphs. All right. So if we're looking at these graphs, here's my question. We know that vertical line tests for functions. What line test do you think will test for 1-to-1 functions? Say it again. Horizontal. All right. Why do you think we would use a horizontal line to check for 1-to-1?
Because then there won't be any repeating.
Right, because it'll see if there's any y's that line up. All right. Guys, you see a pointer up here? All right. Whatever. Anyway, so first off, when you're doing graphs, you first need to see if it's a function first. So start with the vertical line test. So I'll just use my arm. If I run my arm along this graph vertically, is there any point on the graph where two places of the graph cross at the same time? Yeah. So is there any point on this graph that it crosses more than once? At least with my vertical line. No. Because what type of graph is this? It's quadratic. And quadratic is considered a function. All right? Now, it is a function, but if I go horizontally, Are there points where my arm crosses more than once at the same time? Yeah. For example, right here. That means there's y's repeating. All right. So it's a function, just not one-to-one. So horizontal line test. Crap. Oh, it's just too far up. This is why I hate the projector. So it tests for one-to-one. Vertical line test just tests if it's a function. So you always start with the vertical line test first, because sometimes you will run into situations where it passes the horizontal line test, but not the vertical. All right. So always start with the vertical line test, because if it's not a function, you don't even need to bother with horizontal line test. All right. Look at the second one. So run your pencil along the line. We're going to do this in terms of a thumbs up, thumbs down. So do your test real quick. All right. Thumbs up if you think it's a one-to-one function. Thumbs down if you don't think it is. 3, 2, 1, go. It is not one-to-one. Is it even a function? Absolutely not. If I run my, just like right here, not even a full vertical line, but it crosses in 2 places here. It actually will cross in 4 different places here. So that one is not even a function. So this one is a function, but it's not one-to-one. This one is not a function. What about the circle? Do you think it would pass either of them? No. Not even going to pass the vertical. So it's not a function. Now you can write an equation of a circle. It's just not considered a function. What about the last one? It's a linear graph. Yeah, it would. So if I run my arm along it, passes vertical. Run my arm horizontally, passes horizontal. So this one is a one-to-one function. Does everyone understand how to find functions and one-to-one functions from graphs? So again, start with the vertical line test. If it doesn't pass the vertical line test, you shouldn't even bother with horizontal. All right? It has to pass both to be considered one-to-one. In order to be just a function, it just has to pass the vertical line test. All right? So the 2 graphs that are functions are these 2. But this one is the one-to-one. And again, it's because it passes both vertical line test and horizontal line test. So, just to kind of restate what I already said, the horizontal line test, boys, the horizontal line test passes through the graph of function at most one time, then the function's one-to-one. So horizontal lines represent constant y values. Vertical lines represent constant x values. So if a horizontal line intersects more than once, the y value repeated. That's all it does. And this is true also for vertical line tests, just but instead of y value, it's x value. So here's what I want you to do. Take a minute. And I want you to figure out which of these is one-to-one. So take a minute, figure out which of those 4 options is one-to-one. So do your 2 line tests on all 4 graphs, figure out which one is one-to-one. There's only one of them that is. So remember, start with a vertical line test. If it doesn't pass the vertical line test, it's automatically not your answer. The one-to-one has to also be a function. Thumbs up if you're ready. Gonna give you just a couple minutes. All right, with a show of fingers, which answer choice did you pick? 1, 2, or 3? Ready, go. Good. So those of you that picked 3, you are correct. So, why 3? Anna.
Because none of the y or x values repeat.
Right. So, this graph, if I run along vertically, it passes, so I can check horizontal. Horizontally also passes. All right. Now, what's the problem with number 1?
It doesn't pass the vertical line test.
It doesn't pass the vertical line test. This is one of those instances where I said you gotta be careful and check vertical line test first. Because this one does pass horizontal. But that means butt kiss if it doesn't pass vertical. All right. So that's why I say you've got to check vertical first. All right. Because if you don't, I've seen a lot of students in the past, if I ask what's a one-to-one function, they'll do horizontal, and then if it passes it, they stop there. There are graphs that will pass horizontal, but not vertical. It has to pass both to be one-to-one. All right. Now, this last one is more of what we call a contradictory proof. Now, what that means is that they are saying that this absolute value function right here is not one-to-one. Now, what we call a contradictory proof, all we got to do is just show one example where it's not. All right, so I just need 2 values of x, 2 different values of x, that when I plug them into that absolute value function, it'll give me the exact same number. All right, so first off, let's just kind of review what absolute value does. So, let's say I took absolute value of 5 and negative 5. What's the answer to 5? What's the absolute value of 5? Positive 5. What's the absolute value of negative 5? Positive 5. All absolute value does is that anything within its brackets, it changes it to positive. All right? So it's just what it does. So 5, it's still 5. Negative 5, it changes to be positive. All right? So positive will always be positive with absolute value. Negative will turn positive. All right? So, in other words, try x values where you get the positive version of a number and a negative version of a number. All right, so your task, find 2 x values. That'll give you the same number when you evaluate it. So if you subtract that x value from 5, you should get a positive version of a number and a negative version of a number. That same number. All right? Take a minute, see if you can come up with some x values. So just guess and check some numbers. So maybe like pick one number, like pick say 6. All right. See what 6 minus 5 is, and then ask yourself, okay, how do I get the negative of this number? What number do I need to plug in for x now? That's how I would approach it. Just pick a random number, find out what that difference is, then find either the positive or negative counterpart. I will be calling on people, so give it a shot. And there's many right answers to this. There's no one right answer. Just try some numbers, see what happens.
So you just pick a random number and subtract it by 5. But then, like, what is like trying to?
So see how I have absolute value of 5 and absolute value of negative 5?
Yeah.
That's what you want. You want the positive version of a number and the negative version of a number.
So you want the absolute value that always wins.
Because then we take that absolute value and look for positive.
Okay.
And those actual positive values would be actual y values.
Okay. Thank you.
Negative 1 would be equal to 1. So now finding the x value, then you subtract 5. So you found your first x value, x equals 6. Now find the x value that we subtracted from 5. So we keep negative. So again, it doesn't matter what numbers you pick. The only number that I recommend not picking is 5 itself. Because 5 minus 5 is 0, and 0 does not have a negative counterpart. Just pick a number to start with, plug that in for x, and then find its opposite sign counterpart. Or find what value of x would give you its opposite sign counterpart. Because see how x comes first? But would that be negative? Yep, but remember, when you take an absolute value of negative. So x equals 4, 6, and that would be the same y. So that's an example.
Yeah. After you subtract from 5, what did you add? Like,
Then take the absolute value.
how do I do that?
You just take whatever numbers in there. Whether it's already calculated, it's negative.
Like,
So like for example, if you ended up with 5, okay, so after you did all your subtraction, and did whatever minus 5, so say 10 minus 5. You know, that's like such a big minus 5. No, but then let's say I did. So my underhand looking for x that gives you negative 5. So what minus 5 is negative?
can I do a negative?
Yeah, or it needs to be 0 minus 5 is negative 10. Negative 5 is negative 5.
So
X equals 10, x equals 0. All right. Someone raise your hand and give me one set of numbers that proves this statement wrong. Hunter. Negative 10 and 20. Okay, so let's check. So if I plug in 20 minus 5, that's equal to the absolute value of 15, which is 15. Negative 10 minus 5, that's the absolute value of negative 15, which is still 15 when you take the absolute value. So x equals 20 and negative 10, that's a counterexample. It doesn't work. We'll make 1 to 1. Someone got different numbers? Mahogany. 6 and 4. That will also work. 6 minus 4 is not 6 minus 4. 6 minus 5 is 1. Absolute value of 1 is 1. 4 minus 5 is negative 1. Absolute value of negative 1 is 1.
And it has to be in the lines.
So basically, you're doing the absolute value is almost like parentheses. You got to do what's inside of it first before you actually do the absolute value. Anyone got different numbers? Anna?
10 and 0.
10 and 0. Good. 10 minus 5 is 5. Absolute value of 5 is 5. 0 minus 5 is negative 5. Absolute value of negative 5 is 5. All right. So again, there's no right answer for this because the only number that would not have a negative counterpart that I could plug in for x is 5. Because 5 minus 5 is 0. Absolute value of 0 is 0. Well, you don't have a negative counterpart of 0. 0 doesn't even have a positive counterpart because 0 is neither. All right, so that's 1 to 1. So here's what we're going to do. I'm going to give you guys a 4-minute break to use the restroom if you need to. And we're going to at least start inverses today. All right? Make sure you're quiet in the hallways. Yes, I would.
You're worse than me, man. Sick. Allergies, actually. He's like, you need to wear a mask over there. Lord. What did I do? Oh, you mean what did I do? You sound like 2020 ended up showing. No. Oh, she's out there. It's in the back. Honestly. Jesus. And he said that all the time.
You want to go? I'm defeated.
That sucked. There's a Miss Curtin's.
All right, head back to your seat. Let's pick back up at it. All right. Shh, shh, shh. Go ahead and turn your packet to page 16. We're going to at least start inverses today. All right. So, inverse is something that you will see a lot in math. Inverse can mean, it pretty much means the same thing, but we see it in different situations. So, off the top of your head, if you heard the word inverse, what do you think of? Opposite. All right. So, inverse literally means opposite. So, an inverse function is an opposite function of another function. It's its exact opposite. All right. Meaning it undoes it. All right. So, and again, it's really important because sometimes you have to undo another function or operation. So a good example would be if we think operations. What undoes multiplication? Division. That means multiplication and division are inverse operations. All right. They're opposites of each other. What about addition? Subtraction. What about squaring something? Square root. Good. So that's essentially what these are. Inverse operations are operations that undo each other. Inverse functions are functions that undo each other. All right. So again, they're opposites, and they can be anything from additive to multiplicative inverses of a number. So that just means adding and multiplying. And it really helps when you're trying to reverse functions. So you see this a lot when you're solving equations. You see this a lot when you're trying to undo a certain operation or a specific type of function. We'll see this more in Unit 2 when we talk about logarithm and exponential functions. Because technically those two functions are inverses of each other. They undo each other. All right. So we're going to consider these two linear functions. So f of x and g of x. So we are going to first calculate f of 5 and g of 11. All right, so we know how to evaluate functions, right? We're all good on the concept of evaluating. Take a minute, evaluate those two. So I know you guys know how to evaluate a function by now. Take a minute, plug in 5 in for f of x, plug in 11 in for g of x. Over there, underneath the calculator poster. So you're plugging in 5 in for x and f of x, so in the green function. You're plugging in 11 in for g and for x in the blue function. So take a minute, evaluate those two functions. You can use a calculator if you need it. So if you need a calculator, you can feel free to grab one. You're always welcome to a calculator in this class. I am not the calculator Nazi. Well, you know what? It's true. you're just evaluating those very simple functions. You're not even doing an operation to them. You're just plugging and chugging. So again, guys, your EOC is completely calculator active, so this class is completely calculator active. If you want a calculator, by all means, you're not going to hurt my feelings. You're plugging 5 into function F.
Wait, what's the point of doing that if we have the same answer? Oh, go to the water fountain.
All right, thumbs up if you're ready. Yeah, I'll definitely give you another minute. So you're just evaluating f of 5 and g of 11. There's no other operation between the two. You're evaluating them separately. They do not cross. All right, for time's sake, I gotta move on. Check your answer. So for f of 5, you plug it in to f of x. So I have 3 times 5 plus 7 over 2. That'll be 15 plus 7 over 2. 15 plus 7 is 22. Divide that by 2, you get 11. G of 11, plug it into g of x. So 2 times 11 minus 7 over 3. So 22 minus 7 over 3. 22 minus 7 is 15. Divided by 3 is 5. What do you notice about the two values that we got? They're the same as the x values that we initially plugged in, but what's the difference? They switch. They're for the opposite functions. So, for example, what we got for f of x was the original g of x value. What we got for g of x is the original f of x value. All right. Let's try another one, but we'll do this one together because it's a little weird. So, f of 0. So someone raise their hand and tell me how I would set up to solve for f of 0. Anna.
3 times 0 plus 7 over 2.
3 times 0 plus 7 all over 2. So what's 3 times 0?
0.
Plus 7 over 2, so that would be 7 halves. 0 plus 7 is just 7 over 2, and we just leave it like that. All right, someone else, tell me how I would set up for g of 7 halves. So I'm just plugging it in. So how would I set it up? 2 times 7 over 2 minus 7 over 3. So 2 times 7 halves. All right. If you have a 2 in the numerator and a 2 in the denominator, they cancel each other out. You're left with whatever's left over. So what is it? It'd be 7. So 2 times 7 halves. If you add 7 halves and 7 halves, that's the same thing as adding 3.5 and 3.5, gives you 7. All right. So this would be 7 minus 7 over 3. So 0 over 3, which is what? 0. Let me ask you guys this. Did the same thing happen from the first problem?
Yes.
Yeah, same thing happened. So now, this next one is something that you may not have seen before. This is what we call a composition. So let me explain how this works. What you do is that first, you'll find what g of negative 1 is. So you start on the inside and work your way out. Then whatever number we get for g of negative 1, we plug that number into the f of x. All right, so let's do this together. So if I set it up, I have 2 times -1 minus 7 over 3. And that's equal to g of -1. Let me just rewrite that better. So g of -1 is equal to 2 times -1 minus 7 over 3. What's 2 times -1? -2 minus 7. Come on, guys. -9, and then divide by 3. -3. -9 divided by 3 is -3. Now, what we're going to do is we're going to take this -3 and plug it back in for g of -1. So now, what this becomes is f of -3. So replacing g of -1 with that -3, because that's what we got for g of -1. So now we're just going to find f of 3. So 3 times 3 plus 7 over 2. What's 3 times 3? 9 plus 7?
16, 17.
16. And then divided by 2. Oh, wait. Oops. That should be a -3, not a +3. So it should be -9 plus 7, which is -2, divided by 2.
Oh, wait. What, -4?
-2 divided by 2. -1. You're thinking of -2 times 2. So this is our final answer. Now, what do you notice about what we got in the end versus what we started with? All right, match the original. We plugged in -1 initially. We got -1 at the end. So, without even calculating, what do you think my answer is going to be here? It's going to be 5. All right, let's check it. So, we start with g of 5. So, 2 times 5 minus 7 over 3. That's 10 minus 7, which is 3, over 3 is 1. So then I have to calculate f of 1. So that'd be 3 times 1 plus 7 over 2. 3 times 1 is 3, plus 7 is 10. 10 divided by 2 is 5. And we did, in fact, end up with what we started with. So now, with this last one, without calculating, what do you think it's going to be? What is that? Pi. We'll get pi. And I'm definitely not calculating that one, because no. All right, just trust me, you will get pi. So, here's my question. What's going on? What do you think is going on? Just predictions. What do you think is going to happen? What do you think the relationship between f of x and g of x is? How do f of x and g of x connect? What do they do to each other? They undo each other or cancel each other out. So we could say that f of x and g of x are what to each other? Inverses. All right? So, f of x and g of x in this case are actual inverses of each other, meaning they actually undo each other. All right? So, how we know it's an inverse? Inverses literally undo one another. Just like how multiplication undoes division, addition undoes subtraction, square roots undo squares. All right? Cube roots undo cubes, and so on and so forth. All right? So, how we can tell is that if we're given f of a is equal to b for a function f, then g of b will be equal to a. That's just a very fancy way of saying if we're in our original function, we're given the point xy. So if we're given xy in an original function, its inverse or inverse function would be the point yx. So in other words, if you're looking at a graph of an original function and then its inverse function, every point on that function xy will be yx on the graph. In other words, their x and y values flip. So for example, if I had the point 2, 3 here, on the inverse it would be 3, 2. All right, they literally just swap places. So biggest thing when it comes to inverse, if there's one thing that I want you guys to remember about inverses, it's this. Switch x and y values. That's the biggest thing you need to know about inverses. The x and y's switch. And I'll tell you right now, the EOC, they love throwing inverse problems at you. And there's ways you can calculate inverse functions by hand, but sometimes it can get dicey. So in reality, you just really need to look at Desmos and see if they are switching x and y values. Just look at the points. That's all I gotta do. All right. So again, if all else fails, there's one thing you take away from this lesson. Switch the x and y values to get the inverse. That's it. All right. So again, if the original was 2, 3, the inverse would be 3, 2. That's all that means. If the original was 2, 3, the inverse would be 3, 2. So this next example is really easy then, because if this is the point that lies on f of x, which of the following points has to lie on the inverse? So take a minute. Remember, you just switch x and y. In a minute, I'm going to ask you to hold up the number of fingers of the answer choice you think it is. All right, what do you think? Hold them up. It is definitely 3. All you gotta do is flip-flop those x and y's, and you take the signs with them. All right, so the 5 doesn't just automatically become negative. The negative sticks with the -3. So 3 would be your answer. And that's pretty much all there is to it with inverses. Now, another thing that you have to note is the notation. So you guys saw this notation when we were doing our function review, and you were like, what the heck does this -1 mean? In reality, it does not mean you're raising something to the -1 power. All right? All it means is inverse. All right? So if you see this notation, all that means is that it's an inverse function of whatever original function. So inverse function of f of x. That's all it means. Now, does anyone have an idea why they use a -1 in the exponent? Kind of. So, this goes back to exponent rules, which you guys learned back in Math 1. Does anyone remember what a negative exponent does? What are you supposed to do with a negative exponent? Right. So, in other words, you flip-flop its position in the denominator. So, for example, if I had f of x, and it's in the numerator, so let's just say it's over 1. If I make that function an inverse, to get rid of the -1, all I do is take it, move it to the bottom. So this becomes 1 over f of x. Let me ask you this. F of x times 1 over f of x, what will happen? So if I do f of x over 1 times 1 over f of x, what happens? So what's f of x times 1? F of x, and that's for the top and the bottom. Well, if you divide something by itself, what is it?
0.
Nope.
A
It's
1.
1. You subtract something by itself, 0. So, since we got 1, we call this the identity. All right, now you don't need to know this per se. I'm just kind of explaining why we use a -1. Just so it's like, it's not there just for, hoops and giggles. All right? I ain't going to say the actual word I'm thinking of. But, so, we call this the identity. And it means if we get this identity and we divide two things, it's an inverse. All right? So, another way to think about it is, let's say that I had x and x of -1. So y equals and y equals. Well, x of -1 is the same thing as 1 over x. If I multiply these two things together, so x times 1 over x, what happens? So let's say I put this over 1. What's x times 1? X. What's 1 over x? X. So what's x divided by x? 1. Now, do you guys remember how on your parent function graphic organizer, 1 over x was considered an inverse function? All right, that's why this is the parent function for inverse functions. That's essentially what it is. All right. So long story short, if you see this notation, it just means it's the inverse of f of x, and you don't have to do anything to that -1. All right, it's not an operation. You do not need to do anything to it. It's just notation. It's just telling us, okay, if I have that notation, I know this function is going to be an inverse of this other function. All right, that's it. So let's do some more stuff with the inverse. So for exercise 3, they went ahead and graphed this function f of x is 2 over 3x minus 2. So this graph over here is f of x. Now, they want us to evaluate the inverse functions. All right. So, f of -1 of 2. So that means the x value of the inverse function is 2. What's the connection to the... So in other words, 2 would be what value on the original function? If 2 is x on f of -1 or the inverse, what would it be on f of x? The y. So, f -1 of 2 is the same thing as f of x is equal to 2, which is the same thing as y is equal to 2. So how do I evaluate f of -2 on a graph? Or the inverse f of -2? Not -2, positive. Oh my gosh, my brain's not brain. So, what do you think I'm going to do? If I know that for this, coming from this graph, it's the y value that has to be 2, what am I looking for now? So if I have the y from this graph, what am I looking for? The x. So how do you think I'm going to do that? Just how you would do if you had the x value to find the y. So I would go to the graph where it's 2. So y is 2. So I'm on the y-axis and I'm 2. I'm going to slide over until I hit graph. And the corresponding x value is my answer. So what's my answer? 6. So f -1 of 2 is equal to 6. Because on f of x, this is the point 6, 2. If I was to write this as a point, it's 2, 6. Is that not, in fact, switching x and y? Yes. All right. What about f -1 of 4? Or -4? So what am I looking for on the graph? So So if I want the inverse function and evaluate it at -4, on the original function, what am I actually looking for? So if -4 is x for the inverse, that means it's what for the original? It's the y. So I'm looking for on the original graph where f of x is equal to -4, or in other words, y is equal to -4. This is what I mean by, if there's one thing you got to remember about inverses, is that x and y is flop. So they're asking you to evaluate the inverse, but they give you the original. You technically got given the y value of the original. All right? So you find the x value. So take a minute, find the x value for -4 when y is -4. So go on the y-axis, find where -4 is, slide over till you hit graph, and then give the x value at that point. Who thinks they got it? All right, let's go Jaden. What'd you get? How'd you find it? Mm-hmm. Mm-hmm. Right. So I went down to where y was -4. I slid over until I hit graph, which this is at the point -3, -4, and I wanted the x value. So this would be -3. So remember, if this was a point, it would be -4, -3. And that's the flip-flop of -3, -4. So inverses. Now, determine the y-intercept of the inverse function. So, if we're looking for the y-intercept on the inverse, what's the opposite of a y-intercept? An x-intercept. Good. So what do you think I'm looking for on the original function? So if I want the y-intercept of the inverse, and we know that an x-intercept is the opposite of a y-intercept. So what am I looking for on the original? I just said it. The x-intercept. All right. So remember, y-intercept as a point would be 0 and some number. That's a y-intercept. So the opposite, if I flip-flop them, it would give us an x-intercept, which is a number and then 0. So what is my x-intercept on that graph? Where is it at? It's at 3. So this is the point 3, 0. Thus, my y-intercept will be at what point? If I flip-flop them. 0, 3. So f of x is 3, 0. So that means on the inverse, it's 0, 3. Is everyone following what I'm doing? So it's literally just as easy as flopping x and y. That's why I said one thing you got to take away from inverses: switch x and y, switch x and y, switch x and y. That should be ingrained in your brain when thinking of inverses. Now, they then want us to draw the graph of the inverse. So we already have enough points for us to draw a graph. We have 3 points from the previous problems. All right, so we're going to go ahead and graph those points. So I have the point 2, 6. So here, I have the point 0, 3. So right here. And the point -4, 3. So my inverse would look something like this. So this graph right here is f -1 of x. So that's the inverse graph of f of x. All right, last example and then we're done. So this last example, they give us a table and its corresponding graph. So on this table, the table and the graph both represent f of x equals x squared. And they want us to use this table to graph the inverse. So first we're going to fill out this table first. So what do you think I'm going to do for every spot on this table if I'm using the original? Just switch x and y. So we're literally just going to flip-flop the rows. So if I flip-flop the order of the rows, this would be 4, 1, 0, 1, 4, because I'm just copying what f of x is. And then my f negative 1 of x, or my y values, would be negative 2, negative 1, 0, 1, 2. All I did was just swap the rows. If I graph this function, which technically this graph will not be a function, but whatever. So I have 4, negative 2, and 4, 2. 1, 1, 1, negative 1, and 0, 0. So my function looks like this. It is rotated. So what do you notice about this graph? So we already heard that it's rotated. Could it also be reflected? Technically, yes. Over what line? Not quite.
Y over X.
Not y over x, but you're close. Y equals x. All right. So this is review from math 2. But if you reflect it over the line y equals x, if I reflect the original over y equals x, I get the inverse. So it's a reflection over y equals x. Because, and this is just review, if I start with a point xy, this is the rule for reflecting over y equals x. All you do is just switch the x and y. Does that sound familiar? So the rule for reflecting over y equals x is if you start with xy, you're plotting yx. Does that not sound familiar? It does, because that's essentially what you're doing to get an inverse. All right. Any questions on inverses? All right, so we're going to do a little bit more with inverses tomorrow because we're going to go through and fill out that journal entry together tomorrow. And so the rest of the time tomorrow, I'll let you guys do the practice on inverses. If you want to go ahead and start any of the inverse practice, there is a new Delta math. But if you don't want to, you can wait till tomorrow because I'll give you a good chunk of class time to do that. Before you leave, you need to erase your whiteboards, and then I need you guys to hang the graphs back on them for me. So the graphs are in the back over by Miss Davidson.